Hello everyone, welcome to this session. So in this session, we will provide more details of the gradient descent method. So first of all, we will introduce the details of how the gradient descent method works for linear regression. So if you have good knowledge in calculus, you may be interested of this. Otherwise, this is optional, not a requirement of this specialization. So in the last session, we have talked about gradient descent is an iterative optimization method, and the aim is to find the local optimum of a differentiable function. So what we do is that we can consider for y equals to fx, the x in the k plus 1 iteration equals to the x in the kth iteration minus alpha k, so which is a step size, or we call it a learning rate, then multiply the gradient of L, the loss function, at xk, right? So if we write it in detail, is this. So we can see the gradient of L at xk are the partial derivatives of the L with respect to the x1, x2 till xn. So k is the number of the current iteration, and n is the dimension of x. So this is a gradient descent method, how the iteration goes. So this one, the learning rate, we can give it a value, right? So this is a scalar. And the gradient, so how to calculate the gradient, this becomes the center. So let's see, in the linear regression, we plug in the predicted value inside the loss function. So we can see this, right? So note that this x here is not the decision variables. So the decision variables are a and b, right? So these are the a and b. So this x is not the same x as in the last slide, because the last slide we are optimizing fx, right? But this one is L, A, and B, right? So these are the different things. So these xj and yj, these are the samples. These are known numbers. And this j refers to the number of the samples, and there are n samples in total, right? So a and b are the decision variables, and a is a vector. Then we can consider how to do it. We can, if we want to the gradient of a and b, so we should dl, derivative of l, with respect to a1 to an, and partial derivative of l with respect to b, right? So that if we can use our calculus knowledge to get the partial derivatives in the analytical form, so we can see it's like this. So if we look at this equation, we can see here the axj and yj, according this follows the samples, and this I, the ai and xi, these are the dimensions. So a1 to an, x1 to xn. So for example, y equals to a1 multiply x1 plus a2 multiply x2 till a5 plus multiply x5 plus b, right? So this I refers to the number, the index of x, and as well as the a, right? So if we follow these two equations, we can calculate the gradient. We know the step size, we know the gradient, so the loss function can be minimized by the gradient descent method. In the next step, we will talk about the several widely used gradient descent method. So for example, the first one is a batch gradient descent. So in the gradient descent algorithm, so we need to follow these equations to calculate the gradient. This one, we can see there is a n, right? N. So this n can be very large. Sometimes it can be very large. So we need to consider the optimization ability and the efficiency of the algorithm. So in batch gradient descent, as we can see, we calculate the gradient of all the samples, and then we get the average of them, right? Get the average of them. So when we get the average of them, we update the decision variables, A and B, in linear regression. So this kind of method we have the pros and cons. So the advantage is what? So the convergence of this method is guaranteed. But however, this kind of method, it doesn't have so high exploration ability to jump out of local optima. But for this one, for the linear regression, this is convex, so this is fine. Only one optimal, so this is fine. But in some cases, there could be quite a few local optima, like I've shown in the previous sessions, right? So in this way, we want the algorithm to have the higher exploration ability, but a batch gradient descent, we have lower exploration ability, and also it has high memory usage because I need to calculate all of that and say all of the gradient of the samples and save in the memory. Then we can get the average. So when this n number is large, this becomes a disadvantage. The other one, we call it a stochastic gradient descent. So in stochastic gradient descent, this we don't calculate all of them, all of the gradient of all the samples, but we take a sample from the training set in each step. We take a sample, we calculate this gradient, and based on this, we update the model, the A and B value, according to this gradient of this sample. Then I repeat these 3 steps until all the samples are used. Right? So this one we call it a stochastic gradient descent. The pros and cons. Advantage is what? Because each time I only calculate one gradient, so the less memory is required. And this one also has stronger exploration ability to avoid the local optimum to some extent. But the drawbacks is that first, because the model is frequently updated, it's expensive. Because let's say in the BGD, the batch gradient descent, we only update the model one time after all the samples are used. But this time we need to update the model one sample one time. So we need to update it for n times. So this is computationally expensive. And also in this case, the gradient is noisy, and so it causes slower convergence. Then people think of, in the middle method, we call it a mini batch gradient descent. So different from BGD and SGD, so we don't use all the samples or only one sample at a time. Instead, we use a mini batch at a time. So what is mini batch? So mini batch is a subset of the n samples. So we can see it's a fixed number of m training samples, and this m is much smaller than n. So in this way, that the total samples are divided into several mini batch, right? So m is called the batch size. Given this in the MBGT, what we can do is that we first split the data set into a number of mini batches. Then I take one mini batch, not all the samples, not single sample, one mini batch. Then I use this mini batch to get the mean gradient, the average gradient of this mini batch. Then I update the model according to the average gradient. Then I repeat these steps until I cover all the batches. Right, so this is how MBGD works. So in MBGD, that we can have a hyperparameter, and that is m. So how many mini batches do we use, right? So if we use a small m, the extreme value is 1. This goes to STD. So if we use a large value, for example, all the samples, this goes to BGD, right? So normally, a default value of m is 32. So this considers the CPU architecture. So that's why it needs to be the power of the 2. 32 is often used as the default value. So MBGD, we want to combine the advantage of BGD and STD, so it can avoid converging to local minimum to some extent, right? And less memory is used compared to what? BGD, right? And the convergence speed is faster than what? The STD, right? So this is MBGD, so which is we often use the method when we train the model especially when the training sample size is large. Okay, thank you very much. Bye bye.